So I want to talk now about respiratory physiology, and we'll start by looking at some of the mechanical factors that are involved in ventilation. My diagram here shows a lung surrounded by a chest cavity, and this is the kind of diagram that you find in physiology textbooks. Now, the space in between the lung and the chest cavity is called the pleural space, and it looks in the diagram like this is quite a large volume. In fact, of course, this is what the anatomists call a potential space. There's hardly any space at all, and the amount of pleural fluid that we would find in an average human is only around 2 millilitres spread out over the whole surface of the lung. So in effect, the lung and the chest wall are very closely opposed to each other, and there's just the narrowest, thinnest layer of fluid in between the two. But it's useful diagrammatically to pretend that that pleural space is much larger than it is, so we can think about what pressures are within it. Now, you can think of the lungs as being like an elastic balloon. They're inflated, but their tendency is to collapse, just like a balloon would tend to deflate if you would let it. So they want to collapse inwards. But if they were to do that, they would be increasing the volume of this pleural space. The pleural space would have to expand. Now, the pleural space is filled with liquid. And the thing about liquid is that it really can't expand or be compressed. It's an essentially incompressible substance. So you can't expand the volume of that pleural fluid. What that means is the lungs will try to collapse, they'll try to get smaller, and what will happen is that the pleural fluid will develop a negative pressure. And that negative pressure will effectively pull on the outside of the lung and stop it from collapsing. Now, if we think about the chest wall is made up by the ribs, which are all connected by ligaments and muscles, and the tendency of the chest wall is actually to expand outwards. Its elastic recoil is outwards, it wants to get bigger. But again, for the same kind of reason, if the chest wall got bigger, then that would be trying to expand the pleural fluid. The pleural fluid would develop a negative pressure which would pull against it, and so it would be more difficult for the chest to expand. Now, if you think about all of this happening at the same time, the lungs are tending to collapse and get smaller, the chest wall is tending to expand and get bigger, and there's the pleural fluid in between, and that can't expand or contract, it has to remain the same volume. What you're left with is an equilibrium. The pleural fluid attains a pressure value of around -5 centimetres of water. Centimetres of water tend to be used traditionally by the physiologists, but you can convert that into kilopascals if you need to. The point is that the pleural fluid is at a small subatmospheric value. It's at a small negative pressure. And that negative pressure simultaneously prevents the lungs from collapsing and prevents the chest wall from expanding. We therefore have an equilibrium at rest, and the volume of the lungs at rest is referred to as the functional residual capacity, or FRC. Now, that's the volume of the lungs if your glottis were open, but the lungs were neither expanding nor contracting. The whole system is just at rest. If you want to breathe in, the way that you do it is to use the skeletal muscles in your chest wall, and in particular in your diaphragm, to increase the volume of the thoracic cavity. If you do that, you make the pleural pressure more negative, and a more negative pleural pressure will pull on the lungs and expand them further. The increasing volume of the lung will then decrease the pressure inside the lung, which we haven't talked about so far, and a decreased pressure inside the lung, of course, will suck in air from the outside world and you inhale. Exhalation, if you're not exercising, is usually a more or less passive process. So you simply stop contracting your skeletal muscles, and that allows the chest cavity to return and your lungs to return to a point where the volume of air inside them is the functional residual capacity. The purpose of mentioning all of this is to make it clear that the pleural fluid is under tension. There's a negative pressure within it. And under normal circumstances, that's what's stopping the lungs from collapsing. And indeed, if it becomes more negative than normal, it allows the lungs to inflate. This negative pressure in the pleural space becomes clinically significant if you have a pneumothorax, in which case air is allowed to leak into the pleural space, perhaps through a penetrating chest wound. Now, if air can get into the pleural space, that will make the pressure within the pleural space atmospheric. And under those circumstances, there's no longer that negative pressure which is keeping the lungs expanded, and that allows the lung to collapse. And you therefore have a collapsed lung in association with the pneumothorax. So it's important that it's a sealed system under normal circumstances, and that means that the pleural fluid can be at a subatmospheric pressure, and that keeps the whole thing working nicely.